Okay, thank you again for watching. We're going to do chapter 14 now. Share my screen. Okay, so chapter 14 deals with project planning and scheduling. And in this particular chapter, these are the activities that we want to be talking about with reference to objectives, trade-offs, planning and controlling projects, scheduling, constant time networks, PERT, CPM method, and project management concepts. And this chapter starts over on page 341 with the Big Dig in Boston, Massachusetts, which was taking the expressway and tunneling under Boston. Very interesting read, and it really goes into describing some of the problems that they had, but it's really a segue into how a project is defined. A project is not a temporary, is a temporary endeavor that has a specific start and stop time. It's not supposed to be a project that continues to go on for an indefinite time. Over on page 342, table 14.1, you see a few examples of projects that they listed here. And that's certainly not all conclusive, but certainly is a good example. And again, what is a project? Page 342. It's a temporary endeavor. Has a unique start time, unique end time, or specific start time, specific end time. It is trying to complete a unique activity. When you think about a project, certainly there's always, this is table 14.1 again, I'm sorry, objects and trade-offs, objectives and trade-offs when it comes thinking about projects at the bottom of page 342. And there's usually three distinctive project objectives when you think about project, and those three project objectives deals with cost, schedule, and performance. So there's three things that are associated with project objectives, with the first one being the project cost. Certainly is those project costs that you want to be considering, which is the sum of the direct and allocated costs assigned to the project, and it's the role of the project manager to ensure that all costs are controllable. They're defined, tracked, and controllable. The executive objective is managing the projects, which is a schedule, but you must have a schedule which that gives you the baseline from which the project starts, what intermediate milestones that may be in that project that are all pointed towards the end date or the successful completion of that project. And when a project gets behind, typically one of the easiest or one of the most responses you hear a lot is to add more resources, but adding more resources in some cases actually delay the project even further, as you can imagine, because anytime you bring in additional resources to especially a project that's very complex, all those new people now have to have be brought up to speed along with everyone else who's been working in the project already. So adding more people sometimes is not a solution to bring a project back on track, but it is one of those things that typically will occur. And then the third objective of measuring a project is the performance, and the performance characteristics of the project is really defined by the project. It is really looking at how the project is monitored, how it's being developed, what are the quality attributes of to ensure that the specific project objectives are being met. So you have those three distinctive project objectives associated with the objectives and trade-offs of any type of project. And when you think about projects, you see this graph. This graph is a symbolism of table 14.2, where it talks about the project planning, which refers to the decisions required in the beginning of a project. that really is about establishing this general character and direction, and it's really about determining what type of planning that's going to be necessary to ensure that the project objectives are going to be met, to ensure that the resources, human, manufacturing, inventory, financial, et cetera, are going to be allocated, and how those allocations are going to be controlled and measured to ensure that the project is closed out. And you see some of those intermediate activities there on table 14.2 at the bottom of page 343. And again, some of the planning activities that we see in that particular table 14.2, some of the scheduling activities that you see again in table 14.2, table 14.2, and table 14.2. Pretty much self-explanatory, but it's really about the type of decisions that must be made, certainly not all conclusive in this particular table, but some of the decisions that's got to be considered when it comes to managing a project. Then we go into this concept of project scheduling over on figure 14.1, which uses a work breakdown structure as an example. And in this project scheduling, it's that phase of the project where the phase begins with the construction of the detailed list of project activities, which again is called the work breakdown structure that we see there at the top of page 344. Project control is typically through a project manager with a cross-functional team, and a project manager who may be trained to the Project Management Institute's area of knowledge. But you typically have a project manager in a functional team, and part of that project manager's role is to monitor each activity to ensure that work is being performed on the project that are directly allocated to the project, and that where he or she's going to be monitoring the time, cost, and performance in accordance with the project plan. And that project plan really comes into play when they're building their project schedule. Project closing is at the tail end of a project, and that's really where we're looking at formally ending a project, where it includes finishing all the work, closing out all the subcontracts, paying all the bills, turning over the project to the owner or to the project owner, reassignment of any personnel and equipment used on that project. And you see that at the bottom of page 345. And this is where project management is considered a profession, and the Project Management Institute has a certification, which is to help increase that body of knowledge to ensure that a project is adequately controlled, monitored, the costs are maintained, and that you go into dealing with the project implementation, the project scope, the time management, the cost, the quality, the human resources, the communications, what's the risk associated with that, and the project procurement. And you see these activities that's discussed again a little bit further over in table 14.3 over on page 346. Then we go into this concept of scheduling methods at the bottom of page 346. And one of those scheduling methods that we saw in the last chapter deals with Gantt charts, which is it utilizes a form of a bar chart, which you see over in figure 14.2, which is this chart here, which goes into dealing with those activities from the standpoint of using a graph or a network to show the precedent relationships or how one activity is related to the next activity. So they have those interdependence of activities. Typically a Gantt chart is visible, easy to read, easy to understand, commonly used in project scheduling because they are easy to see, widely used. However, one of the greatest downfalls of a Gantt chart when it comes to a complex project is that it's somewhat inadequate because it really doesn't have a lot of the interdependent activities or the relationship between the activities. And for these complex projects, it's difficult to schedule the project initially, and becomes even more difficult if any changes occur to any of the activities. Now, the advantage of a network method over the Gantt chart is that the precedent relationships in the network scheduling are shown explicitly on the network, and hopefully we'll see that momentarily. But you see in figure 14.2, this is an example of a Gantt chart, easy to read, easy to understand, and you can see what activities need to be completed from the time, in this example, from the time they lease a site to the time they move into it. But again, it doesn't show some of the interrelationships that a network method will show. So that net constant time network at the bottom of page 347 is an example where each activity is assumed to be constant. This is typically the easiest case from a standpoint of scheduling. However, we know that in some cases it's a lot more complicated than that, and sometimes we have to use this constant time network methods. And we see over in table 14.4, over on page 348, where we see the activities that needs to be done, what is the description of that, what are the immediate predecessors, and what is the duration in days. And in this type of network, you're talking about the activity on node, or AON network activity on node, which is represented by figure 14.3 and figure 14.4 on page 348, 349. Interesting concept as you look at this, and this particular convention shows that all preceding activity must be completed before another successor starts. And you see in the middle of page 348, we have the early start of an activity based on the early finish times of its predecessors, an early finish, a late start, and a late finish. And as you look at this particular 14.3, we do what is called a forward pass, which is made to calculate the early start and the early finish. In this networking here, we see where A, B, C, and D are the specific activities based on table 14.4, where the 1, 2, 3, and 5 are the duration in days or the activity time that's based on table 14.4. So then as we go through this forward pass, we see now where we added the early start, which is signified by the first numerical value, and the early finished, which is established by the second numerical value over on page 349. So you have the activities and the activity time. Then we added the early start and the early finish when we did a forward pass through the network. Then when we did a then when you do the forward pass, this is the calculations with the activity A being 0, because that's the T of zeros when we start. Then we have the early finish of the A activity, which is the early start activity, plus the T of A, which denotes the duration of activity A. In the early start is the maximum early finish with all the predecessors of A, with the project completion time being the maximum early finishes of all ending activities. And that's that concept of doing a forward pass. You see that being explained more on page 348, then page 349. Then we also do a backward pass, and we do that backward pass to calculate the late start and the late finish, which we see here. The late finish is the minimum of the late starts of all successors of A. In this particular example, or activity A, it could be the other activities as well, but they're just showing here activity A. Then the late start of A equals the late finish of A minus the activity of A of the duration of the activity. And again, that's the backward pass where we're used to calculate the late start and the late finish. Then when we add all the components together, we see we have the forward and the backward pass. In this particular example, is we're writing a business plan, the duration in days it takes to write that business plan, over on page 350, figure 14.5. We're having the all the activities associated with it again, where we have the early start, the activities and the durations of A, B, C, and D, and their duration or time activities, the early finish and the early start. Now we're adding the late start and the late finish of those particular activities. And as you consider, as we're looking at this forward and backward pass, now we can identify the critical path, and the critical path defined over on page 350 it is the longest path within the network from the time it starts from the time it finishes. And it typically will consist of all those activities of early start equals late start and early finish equals late finish. In this particular example, the critical path activities is A, C, and D. For those activities, the earliest they can start to the latest they can start. And as you can see, there's no slack time in this critical path activity. And that slack time is defined as the mathematical difference between the late start and the early start, or the equivalent of the late finish, early finish. And you see that all those activities being annotated in figure 14.5. So critical path definition and slack definition is on page 350 up under figure 14.5. And here is that slack discussion we just talked about on page 350. Here is another table of 14.5 of precedents and times for opening a new office, just giving us, again, the activity, the description, what are the predecessors, the activity time, and the computed slack, or that mathematical difference between the late start and early start. And you see that example on page 351, which goes into discussing this particular activity. Good example to reinforce the concept of critical path, slack, early start, early finish, late start, late finish. Good concepts to read and make sure you feel comfortable with. And here is the figure 14.6, which is page 352, which now kind of takes that table of 14.5 and put all the activities in a graphical representation, again, that shows early start, early finish, late start, late finish, and the activity and the time activity, or the duration, activity time or the duration being the number here. So we see that within the red dots as well. Okay. And then you take a figure 14.7 where that took that same activity and put it into a Gantt chart so that you can see, where we can see the slack, which is signified by the dotted lines, and where the critical path in this particular activity goes through leasing the site, hiring all the workers, and moving into the office. And all those activities under that falls under the critical path, or in other words, non-critical path activities. So you have a little bit of slack time in there where they could slip as long as they didn't move out the critical path time. Bottom of page 14.5, excuse me, excuse me, page 352, page 353, we go into this PERT method, and this PERT method is called the Program Evaluation Review Technique, PERT, which is the network method that's used for project, the scheduling that was developed back in the 50s. And when you think about PERT, PERT usually has 3 time estimates that they deal with for each activity. They have an optimistic time schedule of T subscript O. Then they have the most likely time estimate, which is the T subscript M, and a pessimistic time estimate of a T subscript P. These 3 estimates recognize the uncertainty that may exist in each one of these activities, and this PERT activity or this PERT technique also assumes that the activities or the actual activity times are distributed toward a beta distribution. So the time estimates have a beta distribution, and this beta distribution is skewed to the right with the time estimates that are more likely to exceed the average. And we see that skewness over in figure 14.8 as a graphical representation on page 353. And again, the time estimates have a beta distribution associated with that. Also in 353, we see these estimated of these 3 times and how that calculation is being calculated, where again, we have the T subscript O being the optimistic time, the T subscript N being the most likely, and the T subscript P being the most pessimistic, and where we have the T subscript E being the expected time. And again, this is the beta distribution that's being used associated with the beta probability distribution of these activities. So we see that over on page 353. Be familiar. I would. This is a good example of learning how this particular formula is working, and I think they give us a good example over on page 354 and 353 about how we're doing some of those calculations with that as well as the var of I, which is the variation for each activity on critical path at the bottom of page 353, which is this variance that we see and how that variance is being calculated again on 354 and 355. Then we have this PERT activities goes into the total completion time associated with the PERT activity of the expected time and the variance time of the critical path activities. Now let's talk about the critical path method if we could over on page 356, and that critical path method was developed by E.I. DuPont as a way that it's used to start up and shut down its plants. And since these plants had repeated frequency, the times were fairly known. And as we see in figure 14.9, we see the time cost relationship when it comes to a critical path method, and it has a few definitions that should be known when it comes to using critical path method. We have the normal time, which is the planned activity duration. We have the nominal cost or the normal cost, which is the budgeting cost for the normal time. Then we have the crash time, which is the minimum activity duration for additional cost. Then we have the crash cost, which is the cost needed to achieve the crash time. So you see that in figure 14.9, which is a graphical representation of the critical path method following the DuPont model, looking at the time cost trade-offs between normal activity time, normal cost, crash time, and crash cost, where if I'm using crash time and crash cost, then typically I'm trying to pull back critical path by crashing critical path by increasing the amount of labor that I have on a particular activity to pull that activity back to minimize or to save some time on critical path. It is probably a better way to say that. So you see those discussions on page 356 and 357. Then they give us a good example at the bottom of page 357, 358, how this particular discussion and these 4 time cost trade-offs are being used with some good figures. So over on page 358, here's the graph. Excuse me, this is figure 14.9. Which is on page 356. Yep, 356. So as we think about using critical path time, it's really about how we calculate all the activities on critical path that are crashed to their minimum time so that other paths can become critical. So it's really about how we take the crash time and how we pull critical path back to shorten the overall duration of the project, which may be able to allow us to allocate more resources to other critical path activities. And how much will it cost to obtain any given project completion between the nominal time and the minimal full crash time? It really goes into about how can we go in there and decrease the overall project time by completing some of these subsidiary projects one at a time until we fully reach the crash times. So you see that discussion over at the bottom of page 358. Then finally, we go into these concepts of use of project management concepts. And how some of those concepts can be used. And it really requires a blend of behavioral and quantitative skills, often using cross-functional teams and using scheduling as a part of that to trying to determine the trade-off between how sophisticated or complex a project is going to be and the cost of implementation of that. What type of methods are we going to use, whether it's going to be constant time PERT or CPM, or even more type of advanced type of techniques that we're going to use in order to implement, monitor, and control the project. What type of software what type of software packages are we going to use to be able to take advantage of technology, of computerized network scheduling methods that we can be used in order to ensure the project is going to work and that we can minimize costs, but yet get the project completed on time and under budget. I mean, that's really what the project management concepts are about. That's what using a project manager, developing a very detailed schedule, and why it's so important in doing that. And even up to and considering as part of professional development is becoming certified in project management techniques through the Project Management Institute, where they have a multitude of project certification that is certainly will advance one's professional career in projects. Anything can be used as a project, and the more complex it is, the project, the more sophistication one's skills needs to be as they develop experience and expertise in managing, developing, and implementing projects. So that concludes chapter 14 for this week. And again, thank you so much for watching.